Okay, so the next speaker is Andrea Rocchetto from the University of Oxford, who is going to talk about stabilizers as a design tool for new forms of the Lechner-Hauke-Zoller annealer when we have the technology. Here he comes.
So, good morning, everyone. It is my privilege to be here to speak to you about how we can use insights from stabilizer theory to understand a bit more and improve the Lechner-Hauke-Zoller annealer. So this work has been done in collaboration with Simon Benjamin and Yingli at the University of Oxford. So I will start with acknowledgements, and I would like to thank my funders, Kinetic and EBSRC. So, as we have seen in many talks during this conference, connectivity remains one of the biggest challenges for annealer devices. We're trying to implement this Hamiltonian that, for a reason that will become apparent very soon, I will call the logical Hamiltonian, into a physical system. But unfortunately, nature only gives us for free local interactions, so the one that I've drawn in blue, while the red lines are, more complicated to make on a physical device. So in the last years, we have devised a number of schemes that allow us to construct full connectivity from local interactions. Most prominent are probably the minor embedding by Choi and a pHUC scheme developed by Lechner, Hauke, and Zoller that I'll call also LHZ. Now, what the pHUC does is essentially mapping those two-body local interactions into local fields of a physical architecture. The way we do that, it's quite simple. When two spins are pointing up, well, the physical spin will also point up. And when both are pointing down, we're again pointing up, while the opposite happens when we have spin pointing in opposite directions. So I'm introducing the following notation now. When we have the tilde, we mean the physical spin of our model. Without the tilde, we have logical spins. So what we're trying to map is these two body terms into a single body term of the physical model. Now, the way Lechner-Hauke-Zoller designed the annealer is with this triangular structure, here shown for n equal 4. On the left diagonal, we have single body terms, while all the gray dots are two-body interactions. And we see that our Hamiltonian, now the two-body terms are represented by these single body terms. What is HC? Well, HC is required because as a constraint, we are embedding our system in much larger Hilbert space. And in order to reconstruct the logical dynamic, we need an Hamiltonian that can essentially bring us to a suitable subspace. So what Lechner, Hauke, and Zoller were able to show is that if we enforce parity constraints among closed loops of qubits, so the one you see with the red squares, then we can reconstruct the dynamic. So essentially, our constraint, or these HC, are a sum of parity constraints. And the delta term is giving us how much strong the constraint is. And I will see this is an important parameter of our model. Now, LHZ suggests three ways to implement these parity constraints. First one is the four-body term, means what the parity constraint is. Then they use a different model where they introduce an ancilla qubit, possible, but maybe not quite physically implementable in at least the short term. And finally, and this has been introduced in a paper that appeared in 2016, they have a scheme. They use 3 ancilla qubits to enforce the parity terms. Now, the AQC scheme has 2 desirable features. The first one is that the coupling strengths in the logical model map to single spin energies in the physical hardware directly. So this is quite nice. And also has been conjectured to have an inherent action. And as shown in this paper by Pastarsky and Preskill, we can use powerful decoding techniques like belief propagation to, reconstruct the true scheme, if the true logical model if we have errors. However, the property investigated in a paper by Albers, Vinci, and Lidar in 2016 that has been shown in a real error model to perform worse than the LHZ scheme. However, in their comparison, Albers, Vinci, and Lidar used a four-body the parity constraint were implemented with four-body terms, maybe a bit unphysical. With our work, we give a stabilizer formulation of pHUC. And with this, we're able to first one, second, and formulate new layouts that maybe might be easier to implement in a physical architecture. For example, we'll show a triangular structure. Third, we can create connectivities that are not anymore fully connected, but where we can play with connectivity. And the advantage is that rather than having a quadratic overhead in terms of qubits, we can have maybe an n log n overhead, so we use less qubits. And finally, we can enforce arbitrary order interactions on a 2D grid. Now, our first observation, and I'm sorry for this quite convoluted slide, is that the parity constraints are essentially, stabilizers. So I'll introduce a bit of notation here. So each square is, this plaquettes, is labeled in brackets and is taking the label of the top spin. Top spin are labeled ij, so I are on the right and j's are on the left, and this labeling will become apparent soon, I hope. And same for each node is labeled according to his top left and top right spin on the diagonal. Now, what we are enforcing is that the logical subspace indicated with the ket L must satisfy the following eigenvalue equations. Now, we can do two different things here. We can either say we have even parity, and so Vij are all equal to 1, or we can say we have odd parity. Now, obviously, if it's -1, this is not anymore a stabilizer equation, but the way we are writing the equation in this way is just for, to make things more clear, I would plug the -1 inside the Sij, and we will still get a valid stabilizer equation. So what we have is that the different stabilizer commute, and also that all the stabilizers are independent. This is because in each plaquette we have a new qubit. Now, so the first thing we have to do is to identify the logical Z operators. Here we stick to the convention of LHZ, and we take the logical Z operators to be the qubit in the top left diagonal. Now we need to identify the logical X operators. Now, in order to identify the logical X operators, we take the following commutators, and we're able to show that the sigma X takes the following form, and is essentially a product of sigma X in chains that bounce along our lattice. Here in this figure, we see for the sigma X for k equal 2. And this is, we have now 5, this is a model for 5 qubits, and all the sigma X operators that we can see intersect each other in multiple places. This is quite interesting because we can show that the physical ZZ operators can be obtained by the intersection of two logical X chains. So we see that when the 2 and 3 chains intersect, we have the sigma 2 to 3 interaction. Now, we can write the final Hamiltonian of the system in the following way. HC, again, our constraints, where force the physical system to respect the stabilizer constraint. And then we have to form a logical Hamiltonian, and here we introduce this parameter mu, and mu is essentially a product of the Vij neighboring plaquettes. And by taking all the Vij to 1, we can obtain the original LHZ construction. While if we play with the values of Vij, we can obtain a number of different constructions that I will now survey. So the first construction we can obtain is, rather than enforcing even parity, we can enforce odd parity. What's the advantage of this is that rather than using ancilla qubits or 2 ancilla qubits, we can simply use 1 ancillary qubit. In order to do that, we need to flip the sign of one of the spins, but then, I mean, this is readily implementable. We benchmarked with a small numerical simulation obtained with exact diagonalization how this model with ancilla qubit and odd parity compares with the qubit model. And we see here delta E is the difference between the first excited state and the ground state at the end of the adiabatic sweep. Red crosses odd parity, blue crosses even parity, and we see that essentially we reproduce the same spectrum at the end, so things work fine. But maybe more interestingly, the scaling of the minimum gap, x, is slightly better for the odd parity system. Now, we can use these techniques of the stabilizer formalism to design new lattice architectures that have these interesting connectivities. So the goal is to embed the graph where we have V vertices and E edges. And in order to do that, we will require V plus E physical spins. So what's the recipe? So we start with V spins that represent the logical spins. Then we define E-independent stabilizers. We determine the logical X, and finally the logical Z, so what we have done before. In this way, we can obtain the following funky architectures. First one, rather than using squared stabilizers, so 4-body terms, we can reconstruct everything with 3-body stabilizers. What's the advantage of this? Well, maybe it might be easier to get 3-body interactions. And the way we construct this is, again, by considering the logical X operators and determining their intersection. Now, we can also have a logical graph here on the top that have a tree-like structure. Here we have 21 logical qubits that can be embedded in the physical graph you see bottom left. That requires only 2 times n minus 1 qubits. And while on the right, you see again the intersection of all the logical X operators. Now, another interesting scheme we can obtain is by essentially killing a qubit, so you see it around levels 7, 6, and 5, and obtaining this sort of hexagonal stabilizers that we show can be obtained with only 2 ancilla qubits. The effect of these hexagonal stabilizers is to deflect the logical X operators. And by using these deflectors, we can obtain interesting connectivities like the following. So what we have in this system is that we have a few qubits that are highly connected. And some other qubits that are only 50% connected, and so on and so forth. The advantage of this is that rather than using an n-squared overhead, we only need n log n qubits. Finally, we can construct lattices with high-order interactions. So here again, so all the colored lines are logical X operators, and they overlap many times. And I mean, for at least the top right qubit on the left part of this diagram, they interact 5 different times. So we have 5-body terms. So what are the open problems with this model? Well, as we I mean, I've heard already during this conference, there is an important question: is how much does embedding schemes affect our ability to tunnel through barriers? And this is definitely a quite interesting question, and I've seen an excellent poster here at AQC by Mario Korns, Lachner and Troy that is trying to address this problem. This is still ongoing work, but hopefully we'll have some results soon. And second, it might be interesting to compare this pHUC scheme with minor embedding by using interactions for the parity constraints that are more physical, and maybe using optimal layouts. Maybe the original layout where the first stabilizer is not optimal. Maybe the triangular stabilizer might work better. So thank you very much, and question time.
Thank you, Andrea. So we have time for questions. Yeah, Barbara.
Fairly non-local, correct?
Correct.
Yeah. So the annealing field in the implementation will still be local, will act on 1 qubit at a time. So it means that in order to do a logical X, so meaning going from one configuration to the other, you need more elementary steps of this annealing field.
This is correct.
Yeah. So don't you think, so this radically impacts the way in which you explore the configuration space. So is that something that has been studied by this, can you comment on this? How well, because that's, when I saw this proposal, this is what worried me immediately. I just want to know what people have thought about this. That it really changes the dynamics and it makes it probably possibly very slow.
Yes, I mean, the question is how slow. Maybe it's, I mean, it's slower, but still works. And so the question is trying to benchmark how slow it will get. And I think this work is still ongoing. They haven't yet got any results. But understanding how slow, it's definitely a very interesting question. Maybe it's so slow that we'll destroy everything very soon, but maybe it might not.
Yeah. Well, I mean, it's not a free lunch. I think that's the point.
Well, of course.
There's no free lunch. To get better connectivity, you're paying for something also.
Sure, but it's also a matter of trade-offs. I mean, it's like
yeah, so
it's a price we can pay for higher connectivity.
I understand, yeah.
Okay. Actually, just a quick comment. When you mentioned the ways to implement the LHD architecture, you actually missed one, which is kind of odd since Stefan Zorin, one of the people on there, is actually in your own group, and the person chairing the session is actually one of the other people who designed the this sort of Chancellor Warburton Zorin idea for doing this.
The other person is asking the question.
Yes. Well, it's not really a question. It's just a comment that there's actually another proposal to implement that.
Yeah, thank you for the comments.
Which appeared in NPJ Quantum Information about 2 weeks ago, I believe. Plug. Thank you. Any other questions for Andrea? Walter?
Yeah, I was confused about your n log n overhead. I thought that if you want to embed fully connected connectivity on a basically 2D lattice, you cannot really get rid of the n square.
Yeah, but it's not a fully connected graph.
Yeah,
I mean, only a few qubits are fully connected.
So you are embedding something that is not fully connected, right?
Yeah. I mean, the only fully connected qubits are the pink qubits, sort of pinkish qubits.
Okay.
And yeah, so it's not fully connected.
Any more questions? Okay, if not, let's thank Andrea again. Thank you, Andrea.